Hi, I'm Matthias, the software engineer here in XELA Robotics. In this presentation, I will explain the basics on how to set up the sensors and get the software running. I will cover the options for CAN USB converters and alternatives, the full steps of getting sensors connected to the computer and the software setup process. After that, I will give a bit more details on how to integrate our software into third-party one. And finally, some general troubleshooting whilst I explain some common mistakes. We have tested several different CAN USB converters over the years. Of course, there will be even more compatible devices that we haven't had a chance to test yet. The most common device is from ESD. It is reliable and works well in both Windows and Linux. The biggest problem with it is the price, as it is the most expensive on our list. VS-COM offers competitive devices at much better prices. In Linux it works very reliably, but the support on Windows is a little limited. We are continuously working on getting it to function better on Windows. Peak makes quite reliable devices, but in general they would require their own libraries to be included in the software. We try to ensure that the right version of the library is packaged into the binaries. There are several generic CAN USB converters that can match 1 megabits per second speeds, and one of them is Lavicel's CAN USB. It has been tested to work in Linux as it is compatible with SocketCAN. CANable is an open source converter. It is very similar to VS-COM's device when running on Candlelight firmware. Unfortunately, it is lacking the D-Sub9 port, which makes it more complicated to connect to the sensors. We usually don't recommend using converters without standardized D-Sub9 ports to protect the sensors from accidental damage. This one is listed to demonstrate that there are more possibilities if you are willing to take risks. The reasons for using CAN are following. It is standardized, controllers can be small, you can have several controllers on the same network, you can use sensors with more sensing points, and transfer speed is high for stable throughput. However, it will require extra CAN USB converter to work, and each sensing unit provides data in its own message. In addition to CAN-based sensors, we also offer embed variants. It is good when you have one sensor only. Instead of each sensing unit giving its own measurement separately, all will be broadcast to the computer in one message. Compared to CAN-based sensors, it will be slower, but at the price point, it is the most economical. There are limited sensors you can use with embed. For example, you can use only one 4x4 sensor or few smaller ones. For the demonstration, we will be using ESD's CAN USB 2 converter and Windows environment. In the first step, we will need to get it wired to the computer. Before connecting the converter to the computer, it is recommended to connect the CAN cable between the sensor controller and CAN converter. After that, we can make the connection to the computer and install the drivers if necessary. As a last step, we will need to connect the power plug from the CAN cable to an external 5V power supply. It can be used directly from the computer, but in case of several sensors, the power draw can be too much for the PC to support effectively. With other devices, the process will be very similar, with the exception of embed. That will be detected as USB serial device and assigned a COM port in Windows or serial port in Linux. Embed will not have the external power supply requirement. In Windows, the driver setup is usually automatic. In case it is not, we would recommend checking the manufacturer's website for the latest drivers. Windows will also require Visual C++ Redistributable 2015 to 2019 64-bit version installed, if there is a plan to use our visualization software. Instructions and link for it are in the manual. In Linux, the devices normally use standardized drivers, which makes it a lot easier to connect, with the exception of some peak devices, which will require you to compile kernel modules. There is also a need to install CAN util toolset in case it is not already. Most CAN devices on Linux would require the network to be pulled up. It can differ between the devices. Here we have examples of standard CAN devices and serial CAN devices. ESD belongs to the first one and VS-COM to the second group. In some cases the network names and ports can differ. By this time, I hope that the software has been downloaded from our website and unpacked into suitable directory. The software comes normally with the simulation profile to test the communication of the software. There are two options to get it ready for use. The first one is an automatic one that has some limitations on the sensors it can detect, and the second one is manual, which we'll discuss a little bit later. As in this example we use ESD and Windows, it is important to check that the base network for the ESD device is set to 0. In Device Manager, you can also see if the driver is actually installed, and if not, do it before continuing. The next step would be to run XELA application. By default, it wants to use an ESD device on the basenet 0. There are other options available, but they will require running the application from the command line with extra arguments. Once the application has started, it will read messages from the CAN bus and analyze the sensing point IDs to determine the configuration. In this case, I had one XR1944 sensor on the controller with ID 4 connected. As you can see, it detected this sensor and has written out the model and controller ID. As everything is detected correctly, we can enter Y and press the Enter key. This will save the xserv.ini file into the same directory on Windows or to XELA directory in Linux. In the next step, I will talk in more detail how this file works and how to edit it manually. In cases where the automatic tool is not enough, or when we need to edit some settings, we can make our own xserv.ini file. If there are none, you can create a new file and rename it to xserv.ini. In Windows, I recommend making sure that the file extensions are shown to overwrite it properly. If you have xserv.ini file from the software package, feel free to edit that one. The first section is about the CAN device. The bus type defines what device settings we use. In Windows, it can be ESD, SLCAN, PCAN, Mbed or SIM. The last one is only for simulation, and it generates random values for each sensing point that we call taxel. It is useful only for checking the communication between software packages. In Linux, most CAN devices go under socket CAN, with the exception of some BEAC devices that will require PCAN. Linux also supports Mbed and SIM. The channel tells the software which port or network to use for the communication. In our case, as we use basenet 0 on ESD in Windows, it will be 0. For Mbed, it can be, for example, COM3. In Linux, the devices would be the CAN channel names, like CAN0 or SLCAN0, and for Mbed, it will be the USB serial port device itself, for example, dev DTY USB 0. The visualization section covers detail about the visualization software. Two main properties are shown here, but the newer software will support extra ones. They can be found in the manual. Max offset is used to limit the move of the dots on screen by a specific amount of pixels. In this example, I have set it to 200 pixels from its base position. Max size defines in a similar way the output of the pressure as the size of the dot. I have limited it to 500 pixels in diameter. Those settings will only be used in the visualization software and will not alter any data going out of the server application. Debug section covers experimental and otherwise debugging related elements. The only one that is in general use is SenseBrain, that defines in which way the sensor configuration is presented to the user at the start of the server application. If set to minimal, it will only show single line info of the sensor, like model, ID, channel. In full mode, it will also display the taxel positions. And the final section we will cover here is the sensor one. Num of sensor explains itself and defines how many sensors are connected to the network. So far, we have released 3 versions of the controllers, and the latest one is 3. It can be defined under the CTR_var variable. In control ID, you can define the ID of the controller. In previous example, it was 4, but generally they start from 0. Channel defines the starting STA of the sensor. It is only necessary if a single controller has several sensors. For example, with some XR1944 configurations, which have 2 sensors on one controller, each sensor uses 2 channels. So the second sensor would use channel 2 as the starting one. Model is required as it tells the software which internal or external sensor configuration file to load. Internally, there are only 6 sensor types: XR1911, XR1921, XR1922, XR1844, XR1944, and XR1946. Other configuration files can be downloaded from our website and placed into the same directory where the applications are. In Linux, you can also put them to XELA sensors directory. If more than one sensor is connected, each sensor will have its own section, which will be sensor N. Inside it, you only would need to define what differs from the first one, like channel, ID, or model. There's more detailed information about this available in the manual. The custom sensor configuration files help to set up the sensors in a uniform way. It adjusts the rotation and positioning of all taxels before broadcasting it from the server app. In larger sensor arrays, like with Allegro Hands, it combines all sensors into one, making managing and visualizing it much easier. The downside to these files is that they are not user editable. If you require a custom sensor array, get in touch with us and we will see if we can make one for you. So far, we have been focusing on getting everything ready for the first real test. It's getting very exciting. So now I will cover running the server and visualization software. In this demo I use a desk thumb that has two sensors installed inside, but we will focus on the XR1944 with ID 1. Before we run the visualization, we have to run the server application. In Windows you can simply double click on the executable to open it. It will load the XELA file and then the sensor configuration which is necessary. As we set the sense print in the debug to full, it will show us the full layout of the sensor. Windows will also ask if you want to allow network access for the app. Please press allow. Next we open the visualization software. As we only have one sensor defined in our XELA file, we can simply double click on the executable to open it. In case of more sensors, the executable will only check the first sensor unless it is run from the command line with extra arguments. Now we can see some green dots on the screen. Let's gently touch the sensor and see how well it responds to it. For this clip I did 2 tests. If all seems to work, we can continue to the next step of connecting it to other software. As many developers nowadays use Python, this example will also be given for this. Actually, even our software is written most part in Python. The WebSocket protocol we use is supported by Python 2.7 and 3.4 onwards. We would recommend using at least 3.7. The code will need to utilize several threads to be fully operable. In this example, we set the IP and port variables for the server application. When run on the same device, we will still use computer IP, not localhost, so it can look similar to the one shown in the example. The port by default will be 5000, but it can be changed with the arguments at the server start. Next we will define the dictionary to keep our latest datasets. We also need to define few functions, like the onMessage action that receives data from the server and converts it into dictionary and overrides the variable we defined earlier. Server also sends out so-called welcome message. It gives few details on what to expect from it, like sensor models, and also confirming its IP and port in case there's any extra tool in use between. Next function is more for quality of life. I prefer to define it to make new threads easier. And the last function will be our code that periodically takes data from the last message variable and does the work we need. In this example, we just print out the contents. And finally, we set up the threads and WebSocket client that will be blocking until killed. In addition to the regular direct connection, it is possible to integrate our software with the ROS by installing our open source node. The link to the repository is on our download site. When constructing a new node, you can get the data from our node in a similar way to the shown example. In this example, we want to get the X, Y and Z info of DAXL3 on sensor 1 and print it out before exiting. For this, we import the XELA sensor XYZ service in addition to ROSBY library. We need to initiate the node and give it a name. Then we will wait for the xserv XYZ service to become available. Now we can make our service request by defining the service and format accordingly. Our request can be scheduled in a very easy way by just setting the first argument to sensor number and second one to DAXL number. Once the request gets a response, we can print it out and then safely close the program. There is more info available on the GitHub on what other data to access and how to use data streams. There are times when people just miss a line from the manual or just forget something. Generally, the first step where mistakes happen is that the user is not providing power to the sensors. It is an easy mistake, as many will think that the power comes from the CAN USB converter, but it's not true. To remedy that, the extra USB cable has to be connected to the 5V power source. Sometimes it's also forgotten to change CAN device settings in the xserv ini file, and it will still run in simulation mode and makes it feel like the sensor is crazy. The server always shows which mode it is using to confirm. In recent times, customers have preferred the VSCOM device over the ESD one, but when it comes to the pulling up the network in Linux, they might follow the lines for the ESD device. It is easy to fix by just repeating the steps with correct device instructions. It brings us to forgetting this step altogether. People with a lot of experience with Windows are more prone to forget this, as Windows generally does it automatically, but with its own settings that might not be compatible with the application we need it for. As mentioned earlier with the visualization, there are few requirements for the software package to run. If any are missing, the error usually comes out in the steps covered in this presentation. For the fix, you can just backtrace the steps to the problem area and double check that the right programs and tools are installed. In cases where the simple steps are not enough and more detailed help is needed, we are more than happy to step in and go through all the steps. With email support, we always require basic details of the sensor being used, what CAN adapter is used, OS, brief explanation of what steps have been taken, and output both from the terminal windows and the log files from the software. Those details help us produce the correct xserv.ini file if it's wrong, or find the solution in case something else is different from the general setup. All software related questions can be directly forwarded to me on my email, and also asked if you have any scheduled introduction meetings. Thank you for watching the introduction video, and I hope it has helped you understand the basic setup of XELA sensors and software. Have a nice day.